Hello everyone, my name is Rick van Bruggen from Neotechnology, and here I am again recording the second podcast of this year. I know it's only 2 months into the year, so I've been slacking.
Picking up the pace again.
Yeah, picking up the pace again. And for this second episode, I've invited a returning guest to our podcast, and that's my friend and colleague Alistair Jones from the Neotechnology engineering team. Hi, Alistair.
Hello, Rick.
Hey, thank you for making the time. I know you're a busy man these days, so thanks for taking the time. Alistair, the reason why I invited you back is because I know you've been hard at work in the engineering team on some of the really big new features in Neo4j.
Yep.
3.1 was released at GraphConnect San Francisco last year. Or no, it was actually announced and it was released a little bit later. But one of the biggest new features in Neo4j 3.1 was the new clustering architecture, right?
Yep.
And that was part of what you and your team were working on?
Yeah, it was a really big thing for us, actually. So we've been working on this area for nearly 2 years, actually, building this new clustering architecture.
Wow.
And as you know, Neo4j is a cluster database. Designed to run over multiple servers. And we've had that in place we've had clustering in place for 6 or 7 years in Neo.
Yep.
This is the biggest change we ever made by miles. It's a huge upgrade of all the technology around the clustering.
Wow, I remember, like in version 1.8, it was like Zookeeper that was doing some work.
We had a small change in the 1.9 release.
Yep.
Back in the day.
Back in the day, yes.
This is a much bigger release in 3.1.
So what's it all about?
So the first part of it is getting up to date. So the world around us has moved on, and one of the great things about doing engineering at Neo is that we can take research from academia and actually apply it. So reasonably recent stuff that if people love to read the academic papers and blog about it. We can go and we read all those, and some of those things we can put them fairly quickly into the product. So for us this time it was doing the Raft protocol, which is a consensus algorithm.
Okay.
So what that means is getting agreement between participants, so computers in this case.
Yep.
We
members of the cluster, right?
Yeah. So in this case, it can be different servers in the cluster, and getting consensus between those servers when the servers themselves and the communication between the servers is potentially unreliable.
Yep.
So you need to account for that unreliability in the design. Now we already had we know a little bit about consensus algorithms because we previously, back in that 1.9 release, we implemented Paxos.
Okay.
And at the time, that was the kind of state of the art thing to do. Raft, you could argue, at some theoretical level, is the same thing, but it's much more clearly structured.
Raft is the new consensus protocol, right?
Yeah, exactly.
Yep.
So it actually. It's from Diego Ongaro, is the lead researcher in this area, and it's really impressive how it's described. It actually aims to be simple to understand and to explain, and that makes it really really good to implement because you can be very clear about what you've done. You can see the direction that you've gone in. So we changed from one consensus algorithm to another.
Yeah. Which is a big change.
Which is a big change, but it's also architecturally it's totally different because previously we were using Paxos to agree on membership of the cluster.
Yep.
So actually a very small amount of data. There aren't that many servers; they don't go that often.
Yeah.
Now what we're doing is we're using Raft and we're using it for every single transaction in the database. So every single node, relationship, property you create in the database, it goes through the Raft protocol. You've got consensus across the cluster. And what that means is that every single change is agreed to by a majority of the cluster. Okay. So no matter what happens in terms of loss of connectivity or failure of a minority of the servers, still the cluster as a whole agrees on what the state is as you move forward. So
sounds a bit like open heart surgery to me.
It's quite a major change, but it's actually really nice. Once you've got that super solid foundation, you can build a whole load of things on top of it. Okay. So it's extremely solid for storage. It's like the most reliable we could make it, and it stores every single transaction in this replicated log across all the members of the cluster. And also, as the membership changes, that's agreed through the protocol as well. So you know at every time who the people were, who the servers were, who were allowed to vote on transactions and to get them committed. So it's the whole thing's very tightly integrated into the core of the clustering.
So I would never claim that I understand everything about it, but what I've read is that it's very different architecturally in terms of previously we had masters and slaves. Now we talk about cores and edges, right?
Yeah, so that's the second part of this, is that we were aiming to have much larger clusters than people had previously been running in Neo.
Okay.
I think it's been around for a long time, and previously people used to think of having 3, 5, 10 servers as being a large database cluster.
Yeah.
Now people want to run hundreds of servers, and we have customers and users running in 200 servers in a database cluster.
Yeah.
We want to be able to go higher than that, and the consensus algorithm that we were using before, the design of it, or the membership, it had a kind of it had a sort of limit on, or there was a kind of it was hard to get to that scale, and the reason is that all of the servers had to be aware of each other and what they were doing at any stage to basically make sure that they hadn't disappeared.
Sure.
So that led to heartbeats.
Yeah.
Going from every server to every other server, and that ultimately gets very expensive when you have a large number of servers. It also gets very difficult when you're committing across the majority of the servers, because you have to wait for a large number of them to come back before you can say, yes, this is now safely committed.
Yeah.
So just having one huge cluster of raft servers is not a good design for that kind of hundreds of servers or thousands of servers at a time. Yep. So we came up with a new architecture, and what we do now is we divide the cluster into two groups. We mark some of the servers as being in what we call a core.
Yep.
Core servers participate in Raft, and they are about safety. They're about storing your data durably.
Yep.
Secondly, we have a potentially much larger group of read replicas. And these are servers that are for running your queries on.
Yeah.
And
read queries, not write.
Yeah, read queries. So you don't have to worry about safety here.
Yeah. And
the idea is these are about, they're disposable, they're where you can scale them up and down, have, when your web traffic is high in a certain time of day, have just more and more of them.
Yep.
Tear them down, tear down your cloud instances when it's quieter, and you can adapt to the shape of your traffic with the read replicas.
Yep.
What's interesting is that the name read is that we're doing more service of reading. Why does that make sense in a database? Has that helped you in a database to have more read-only things? Surely you need them also to write. Well, that's because of the shape of graph data. It's because actually when we look at the, I'll show you because it's a nice slide. We're audio only. There's a really nice slide that shows kind of how we see people do stuff with graphs. And what you notice is that the write queries, the updates, tend to be quite small.
Local.
Very, very local, like 2 or 3 nodes in relationships, up to tens, maybe 100 things in a transaction. Whereas on the read side, the whole point of graphs is to go really fast, and people go a long way. They traverse a lot of the graph in a read transaction. So they're doing thousands, hundreds of thousands of relationships in one transaction. Now, that's very fast, but it still takes resources. It takes memory bandwidth, it takes CPU to run these queries.
Sure.
And that's what people are really hammering their graph with, thousands of these, each very big queries. And that's an enormous amount of computational load. we want to spread that across a lot of servers.
Yeah.
And this is a way to do it. Have loads of read replicas that can handle that traffic for you. So it is really helping you in the kind of graph applications. It's a very specific architecture to the type of system that we're building.
Very cool. And so, as I understand it, the cores, so they're all about the safety and about writing to the graphs, and the edge servers are all about reading. Is there any downside to this? Is this all good? Good news show all the way around, or are there some things that we should take care with?
So there's one thing that's a slight challenge here.
Yep.
The people when they're deploying these type of applications is that the transaction is being pushed out from the core out to the read replicas.
Yep.
And there's some delay in that happening. It's very small, but there is some delay. So people call this eventual consistency.
Yeah.
And this is something that we're aware of from lots of modern sort of web systems, that you get into this kind of eventual consistency situation. An example of this that could kind of catch you out is say you're a user, you create an account or you make a booking. That's a write transaction. It updates the graph.
Yep.
Then when you come to you refresh your page, we try another operation. It's a read-only operation. Maybe you hit a read replica that hasn't quite seen your update. So as a user, it almost appears like the thing you just did has disappeared, like you've gone back in time.
It's the read your own rights problem.
Yeah, you haven't. You're just like, I can't remember. So what we did at the same time as this is we actually added a whole new feature that became the name of the whole clustering architecture. Yeah. So this is why it's called causal clustering, because we added in a feature of causal consistency.
Tell me more about that, because I don't know what that means.
Okay, good. So causal consistency. So it's actually something that's been, again, from researchers, some academic and industry research in this area, but it's not very commonly implemented. There are only a handful of other implementations out there. Yep. And what it's about is trying to represent what causally has happened in the user's application, so the cause and effect of the changes that you've made. Mm-hmm. Practically, it's very easy to use. What happens is that when you update the graph, or when you touch the graph in any way, the database can give you a bookmark, and this bookmark represents the latest thing that you've changed or the latest thing that you've seen in the database. And then when you make another request to any other server in the cluster, you can supply that bookmark, that same bookmark, and the database will make sure that it has at least as up-to-date a state as the bookmark represents. So the bookmark is just a little string,
okay,
and it comes back through the database driver into your application code. You can store it in your application server, or you can hold on to it temporarily while you make another query, or you can send it all the way back to the client. You can send it back to your web browser or your mobile device, and route it back ultimately to database.
So that basically assures that the client of the database always takes into consideration everything that it caused.
Yeah, it prevents you from going back in time.
Yeah,
is what it does. And it supports a totally stateless architecture between everything between the user and the database. The database is storing state.
Yeah.
Why should you need to store it anywhere else? So this is this idea: you don't need sticky sessions. You don't need to worry about sophisticated routing. Just have stateless application servers, pass your bookmark around, and you get causal consistency. That's the idea.
Wow.
And we've tried to make this even easier to use by building some of the primitives, the kind of passing backwards and forwards, keeping track of things, is built into database drivers. So in 3.0, we introduced
Vault drivers, right?
Yeah, the Vault drivers. So the officially supported native language drivers in your.
And so the new version of the drivers supports this bookmarking, and that gives us the causal
consistency. Yeah, exactly.
So let's talk a little bit about the future. What's coming up. What are you working on now, and what keeps you up at night?
Yeah, well, so the next stage, I mean, it's kind of following on logically from where we are now. So the next stage of this is to be, it's a kind of how people actually deploy this stuff. And these days, not just a cluster of servers that are running it, that you're using it to run a database. It's also it's also servers across multiple data centers and multiple regions around the world, around the country, or around the world. So that's what the cloud environments make it very easy to do, to have geographic distribution. Yeah. And we are taking account of that that feature in the product, or that usage in the product. So what we're going to do is make the clustering aware of data centers and how they're organized, and allow the client to give hints about how might be the best way to serve it. So that means that you can be you can do your reads from a server that's very close to you with a low latency.
Yeah.
And you can support fault tolerance across data centers when one of them goes away, or explicitly recover in a disaster recovery zone, or so, all of these different operational scenarios. So,
is that something that's coming up in the next couple of versions of Neo4j?
Yeah. So in the next couple of versions, that's the stuff's going on. And again, it's to be seamless all the way through the driver. So you can write your application once for Neo4j on your laptop, and then it should move forward with all the load balancing built into driver.
That's very cool. I have one more question. Don't you miss the visualization stuff that you were doing before?
Yes, I always miss the visualization, but I try to find some spare time to get back into it every now and then. So,
very cool. Well, thank you so much for spending the time, Alistair. I mean, we want to keep these podcasts fairly short, but I'm sure we'll include a bunch of links to the documentation and the blog posts that we wrote about this topic. Really appreciate you making the time, and look forward to seeing what's up next.
Thank you very much.
Thank you. Bye.